It's also a pleasure to be talking about the SDSS5 LVM now finally that we are getting data. This is what the LVM site looked mid-pandemic, as you can see with everybody masked. This is 2021. This is what it looked like last summer. And this is the inside of the enclosure now with all telescopes operational and in survey mode. And I'm really here just a spokesperson for a very, very large team of very dedicated people who've worked tirelessly for almost 8 years to build this project and get it on Sky, get all the software written, get everything designed, write documentation, write science requirements documents, go through reviews and get money and whatnot. So I'm grateful for everybody here on this list. And I'm also advertising this paper because this is the first paper describing the overall project, which is going to be submitted sometime this week, I hope. If I have an hour, I'll get this out of the way. And there's a few other technical and science papers coming as well at the same time. So a quick word about SDSS5. Actually, this is 2027, is a 2-observatory multi-telescope survey of the Milky Way mapper, which is observing a lot of Milky Way stars with Apogee and the BOSS instruments in both hemispheres now. A quasar reverberation mapping program, again, in both hemispheres, and the IFU survey of the local group, which is the local volume mapper, which is the project that I am working in. Very quickly, the idea there is, star formation is a multi-scale process that goes from, fractions of a parsec, the scales of stars and stellar winds and solar systems, to scales of, fractions of a parsec through H2 regions and scales of about 10 parsec and up, molecular clouds, maybe 20, 50 parsecs, 100 parsecs or so with bigger cloud complexes and structures within galaxies up to megaparsecs where we are, see the effects of feedback, not just by AGN, but also galactic outflows, interactions with the CGM and all of that. It has a huge dynamic range of 12 orders of magnitude or something like that, that sets the structure and chemistry of galaxies and regulates their growth. So I am in particular coming from manga. I actually, just like a speaker this morning, started my life at high redshift and worked on local galaxies, and now I'm working on the Milky Way, and soon I'm going to be doing planets probably. The trend continues into the future, but sort of, view myself as a little bit of an outlier in this community. I come from a global view of galaxies, and so after manga, we've decided to, instead of looking at even larger numbers of galaxies, we rather want to drill down and understand the physics of the individual ones. And so this is sort of an overview of the IFU landscape as it was presented to us a few years ago when we started this. Manga and Sami live here on this side with about a kiloparsec resolution, but tens of thousands of galaxies or 10,000 galaxies. Khalifa, another very successful project, lives sort of down to 100 parsecs or so and has observed a few hundred galaxies. FANGS, which is now producing wonderful results using space telescopes and ground-based observatories, goes down to about the scale of clouds, about 50 parsecs or something like that, maybe 20 parsecs on a few of their objects. And the idea with LVM is to go way this way, right? Where we resolve not just individual objects, but the structure within individual star-forming regions and its 2 regions, and we resolve all the filamentary structure in the ISM, the shocks, and the exciting kinematics. We are at 10 parsecs in the Magellanic clouds, and we are about at 1 parsec or a tenth of a parsec in the Milky Way. Okay, so why are we doing this? Well, because feedback emerges locally and propagates globally. And so we want to resolve galaxies down to individual sources of feedback, while at the same time maintaining a global population view of all the regions and clusters and young stars that contribute to feedback processes in a single galaxy, so we can start, making time series analyses of these regions, perhaps understand how they interact with their environment and how they feed back to larger scales in these galaxies. Now, high spatial resolutions of parsec scales are only possible in very nearby objects, right? And at the same time, full galactic coverage requires extremely large fields of view. We're talking degrees, okay? So that is what we're going to do. LVM is an integral field spectroscopic survey of the Milky Way, local group, and a few galaxies in the local volume. It's the first IFU survey to cover actual fractions of the sky, right? All of 10,000 manga galaxies were half a square degree. We're talking about a steroid here. of sky. It's the first IFU survey to covers full galactic systems while at the same time resolving individual structures within them. And by that I mean star-forming structures. And the idea there is to sample the energy injection scale and resolve clusters, clouds, and all the way up to kiloparsec scales. And essentially, if you want to think about this from the point of view of theory, we are the subgrid physics survey that you feed into your simulation to understand, once you set a scale for your subgrid, modeling what the inner across that boundary really looks like. So our spectroscopy spans the whole optical range at a resolution of about 4,000. We cover strong and aurora lines, and there's a list of lines that people contribute to with everybody's favorites are in there. So the point is we cover the whole optical window, and we are sensitive enough to essentially have access to the weak aurora lines in every spaxels, in the H2 regions in the Milky Way, and almost everywhere in the Magellanic Clouds as well. The idea is to have bench-mounted and environmentally controlled spectrographs. So the instrument is extremely stable, so that we can, despite the resolution not being the 50 or 20,000 that you want to in the ISM study, still get very good access to kinematics and broadening, and very good calibrations. We are the first IFU instrument that have fibers that do not move. Okay, even our telescopes do not move, as you will see in a second. We get very nice flux calibration and widely applicable, very well calibrated data. This slide I'm not going to go through, but the point is it's a very timely project where we have multi-wavelength data at about the same spatial resolution and similar coverage to what we do in LBM from the radio all the way to the X-ray regime, both in the Magellanic Clouds and in the Milky Way. Okay, so what are we doing? First of all, our IFU, the red hexagon up there, contains 1,801 fibers in 25 hexagonal rings, and it's about the size of the full moon. Okay, so we cover the Milky Way essentially in two boxes. There is a thin and long box. This is 8 degrees wide, and a thicker box that is, I think, 18 degrees wide. And the idea there is to have the most simple selection function we can imagine. If you have a simulation, you can select the same box in your simulation and show us your radiative transfer and what emission lines you're getting. Okay. Then we are covering Orion just because it's the nearest star-forming region, and we cannot not cover Orion. And we cover the Gum Nebula because it's the same region where we cover Orion. And then we have the Magellanic Clouds. Sorry, the Milky Clouds. I need to get used to that. The Milky Clouds, I think I've cleaned my slide, but I'm still saying Magellanic once in a while. And we have this grid of high galactic latitude fields that covers all the visible sky, just to see what's going on outside of the disk. Here is a typical Milky Way region at a distance of about a kiloparsec, where we get about 1 parsec per spaxel, 10 parsecs per spaxel in the LMC, and a fraction of a parsec in Orion. And this is simulated images. I'm going to show you real data in just a second. And here's a zoom in for this audience on the LMC, where we get about 1 million independent spaxels, and that's the coverage. And here is the same for the SMC. Now, the instrument is a really funky instrument, and it's very nice, and I encourage you to go read the papers by Nick and by Tom that shows you what's going on here. I'm just going to flip through this rather quickly until I get to this point, and it's a collaboration between many big institutions. Here's the anatomy of one telescope, and the idea is it's a siderostat, okay? These are 2 flat mirrors, no power, optics is moving in the system, and a bench-mounted telescope, K-mirror rotator, in a fixed fiber bundle, okay? So the only thing that moves here are 2 flat mirrors. All right, let me skip that and start showing you a little bit of data. Here's the Milky Way. Here is one particular nice region of the Milky Way. I think that's a Shasta image. Here's our data, okay? This thing is about 19 tiles across. It's 2 degrees wide, 35,000 spectra. And here is one of these spectra. And if you go and look at what lines you find, you can see collision excited strong lines or combination lines, Paschen lines, and temperature sensitive aurora lines. This is a fairly cool region, right? We don't see the oxygen aurora line, but we see nitrogen and sulfur and the red oxygen line there. So it's nicely very weak temperature sensitive lines everywhere. This is Orion. This is this is the simulation. And here is the electron density from the oxygen doublet in that region. So you see how it looks like. And here is most of our data on the core of Orion. This is about 200,000 spectra. And what we're showing here is high ionization in magenta, the sulfur 3, sulfur 2 in sort of bluish, and H alpha in sort of the brown tones underneath. Just so you see what the scale of the data is. This is 5 degrees across. It's probably the largest IFU map ever shown anywhere. And again, this is the LMC. This is the data we already have on the LMC. So we see we've covered quite a nice fraction of it. This is H alpha. I'll upload the slides so you don't have to take pictures of them. Or I have to send them to you as well. And here's a zoom in. So you see all the structures that I promised you in the ISM. This is just H alpha here in this particular case. The survey is going very, very well. This is what we've covered so far. In our various targets, just to show you that we are in full survey mode. The timeline, we started November 23. We likely end in May 27 when we run out of money. The first public data release is going to be end of 2025 in data release 20. But of course, if you are Sloan members, and maybe people here are, the data is already there for you to explore on the SAS. Reduced data is already on the SAS. We have both a data reduction pipeline operational and the data analysis pipeline, which gives you stellar fits and emission line measurements and everything you ever wanted to know about these things. We measure about 200 emission lines. We have kinematics and a number of other measurements. If you are a theorist, then please get involved. It doesn't matter whether you simulate individual objects like the Rosette Nebula, or if you simulate whole boxes on parsec scales or kiloparsec scales, please come join us. We need more theorists involved in this effort. And here is my summary slide. And I thank you very much for inviting me to come here and present this to you. And this slide just gives you sort of the one slide overview. And if you're not members of SDSS5, it's time for you to join. Thank you.
Thank you. Questions?
Cal Barger at TCU. So Niv, are there data cubes and data products that are available similar to like manga type stuff?
Yes, everything is on the SAS.
Yeah, I don't know.
Everything is on the Science Archive server.
Okay.
You can get everything. It's reduced. There's no cube. I mean, there's software to make cubes, but we haven't put cubes on the disks yet because they are terabytes in size.
Okay. Okay. So not cubes and no products yet then either.
No, there are RSS files with reduced, fitted, everything spectra and line measurements.
Okay, so only the spectra with measurements, or not measurements like this? Like
yeah, you have tables with measurements of 200 emission lines, and you have also the full spectrum.
Okay. Okay. Cool. Yeah.
Would it be useful for it's focused on the gas emission, but what about stars?
Not necessarily.
Not necessarily. So how many stars are there?
I'm just telling the ISM story for brevity reasons, but actually modeling the stars, in particular, I'm very much interested in actually taking the CMDs that we've seen today and comparing them to the, just assigning spectra to each point on the CMD and comparing that with the spectra, the integrated spectra we get. We know ground truth. We're not worried about stochasticity in a star cluster, not knowing what the most massive star is, not having a fully populated IMF, and so forth. So yes, the stellar science is absolutely there.
And if there is like 1 star per spaxel, sometimes what would be the limiting magnitude in that case?
Or so if you want 1 star per spaxel, then you're probably something like 13th, 12th.
So yeah, in that sense,
Something like
it's
that?
very bright, but the
Well,
power comes from the integrated.
So for example, our spectrophotometric calibration stars, they are 9th magnitude, and they dominate the spaxel by a factor of 100 or more.
Okay, we're just gonna take you off, if that's okay, but you can answer this last question that
Sorry.
we have.
Oh,
While
yeah,
Joanna
just
sets up.
unplug me. There you go.
Okay. See if this works.
Yeah, yeah.
Okay, sorry, Neve, you have one more question.
Oh, I'm
while
sorry,
she
yes.
sets up.
Does it
Yi
still
Fei
work?
from CFA, and we are doing the 3D photo animation code, and I'm the kind of serious,
Huh?
maybe you need, so we should talk. And the question is about how many nebula in this kind of survey will reach the resolution and down to 0.07 as Orion, or 0.1.
Well, Orion is the closest region, I think. And so if you want that resolution, there's not going to be that many, right? But if you want below a parsec, there's going to be tens, if not 100 of them.
Is it limited to the southern sky?
Right now, we are operating from Las Campanas. So it's limited to the southern sky. We did have plans to do 2 observatories, but the pandemic killed half of us. So hopefully in Sloan 6, if we get the money, we'll go north.
So no chance to observe Cygnus X, for example.
Right now, we can't observe Cygnus X, but hopefully in the future we will.
I'm not on Zoom. Should I go on Zoom?
Okay, well, while we wait for Joanna to get set up, I think we can take one more question.
Hey, so I was wondering, what is the typical resolution, spectral resolution? Can we study diffuse gas also around
Yeah, absolutely. The resolution is 4200 AH alpha.
4200?
Thank you. This is all gorgeous stuff. I was wondering, are there going to be like official metallicities released as a derived product at any point? Like if I go out and do something and measure metallicities and you come out with official ones and I look bad, is there a way of avoiding that?
So the answer is maybe.
Better.
So there's people throwing metallicities around the team, obviously.
Oh,
In terms of releasing
fine.
them, we can release 0 or 10 different metallicities, right? The question is which ones. And so how you do the direct metallicities, how you do the, whatever. So there's many calibrations, and eventually I think we'll solve the calibration issue. And then maybe there's going to be a final metallicity that we release. In the meantime, I think that is something that it's best to come work with us to see what model dependent quantities we want released publicly.
So I would love direct measurements, but I'm not trained to do that. So
so I don't know why it's doing that.
When on 2025
It's in a Dropbox. It's in a Dropbox.
will be
Yeah.
the first release?
Yeah, okay.
You have an idea of month? What month?
DK, it's December, right?
Should be December end of
Year.
year.
Yeah.
Excellent. Thank you.
A song until they're ready.
Sorry. Sakowska.
Take more questions.
Yeah, V3. Yeah, there you go. Perfect.
Okay, let's thank Neve again. Enjoy the song.
It's just a
Yeah, I think you want to not hear me sing.
big intro.
Okay,
Okay, so it pops up now. How can I make it like present mode?
I think
I'm not a Mac person, so.
Did you upload your file?
Sorry, I feel like
No,
I'm
don't worry
not
about
tech
it.
savvy here. There we go. Yay!
Great,
All right.
thanks. We have Joanna Sakowska, who will tell us about the star formation history of the SMC's shell, and I'll give you a 2-minute warning.
Awesome, thank you. So first of all, I'm so happy to be here. This is really exciting. I'm Joanna. I'm a finishing PhD student at the University of Surrey on the Diversity in Physics Fellowship. So I'm finishing up, so I guess I'm on the market. But I'm actually really excited to talk about this now after the discussion we had in the discussion room about the star formation history and the synchronicity and tidal disruption. So I would like to start with this picture of the SMC. It's one of my favorite images of the SMC. It's, if you can see here we have the main body, but what, and that's great. But what we're really interested in is the outskirts. So the outskirts have been highlighted to show a plethora of star structure around the SMC. So for example, here we have stars towards the LMC. So the LMC should be around here. Up there, we have a shell of stars. Looks like a shell, which is the focus of this talk. And in general, there is a lot of structure around the SMC in the form of star clusters and really cool stuff. So now, if we take a star formation history of these structures, such as the shell, we can gain valuable insight into how did these structures form? Why are they there? Did the LMC have any influence on them? So this is the aim of the talk. And I won't talk too much about SMASH because it's been really lovely, well talked about now by David, but this is the dark energy camera. So SMASH is a survey with the dark energy camera in Chile. The dark energy camera has a beautiful view of the MCs. And just to sort of give you some context, the dark energy camera was quite revolutionary for star formation history studies because traditionally we had the Hubble Space Telescope, which you'll hear so much about today, has done fantastic work with really deep CMDs on the on the MCs, but what they lacked, unfortunately, and this is where dark energy camera really complements and SMASH survey complements, is coverage. So the DECAM, we can obtain CMDs that reach below the main sequence turnoff, which is really important for star formation history calculations and comparable depth, whilst giving us that contiguous coverage of the MCs. So with that survey, what I did, so the aim of my PhD in general is a updated star formation history of the SMC with SMASH data. But this talk, I'll focus on the shell structure. So this is the CMD of the shell structure with SMASH data. It's really quite beautiful, I think. There's so much to say about this. So first of all, the CMD goes well below the main sequence turnoff about here. Crucial in breaking the age metallicity determination, so you can date the ages and metallicities of the stars with good precision. Second of all, the CMD has all different types of stellar populations in it, so we can already say that the shell has you know, it's not just young, as we see by here. This is quite a it has a very prominent young upper main sequence, so a lot of young star formation, but it has a plethora of other stellar populations. Now, what we can't quite see here so well until we look at the red clump, which is theoretically a very point-like feature on the CMD, which is why it's a good distance indicator, is that the CMD is affected by line of sight depths. So if you look here, in black dashed is the observed red clump luminosity function, and in blue is a model red clump luminosity function, and we can see that they don't match well. We can see that the model is a bit more peaky, and it doesn't look like it's such a big disparity for the shell, but I don't have a clicker. The reason why we consider the line of sight depth and we want to amend this gap is that actually, if you look at this map of the SMC, the SMC's main bodies around here, there's a lot of line of sight depth in the northeastern SMC, up to 20 to 30 kiloparsecs. For a galaxy that's only 60 kiloparsecs away, a 20 to 30 kiloparsec line of sight depth is quite significant. So that is why we decided to, in order to have a homogeneous methodology, to include the line of sight depth in the calculation. So a quick note on the CMD reconstruction method, how we obtain the star formation history. We have the observed CMD. We study all the different regions on the CMD in great depth. So we have the main sequence here. We have the upper main sequence, and we take a model column magnitude diagram And essentially the idea is we want to reconstruct what we are seeing with theoretical models. So the model CMD already has a degree of observational effects added from crowding tests. So you know how much, how accurate your photometry is. And from that, you obtain a solution and a star formation history. So, okay, so how do we add the line of sight depth? So what we do is, because the red clump is, the shape of it is really affected by the Asian metallicity, first, we obtain a star formation history. Okay, so that's what we usually do. Great. We get this, and we get a solution red clump. So the solution red clump is like a model red clump. And what we now do, so that's in blue, is we inject, we simulate a line of sight depth in this model. So it's increasing so that it starts to match the observed red clump. So then we take that information and we solve for a star formation history again for the final SFH. And that line of sight depth is included in the model we solve with. So then we obtain a final star formation history. And although it doesn't maybe look that significant here, I hope I can convince you that it does work. So here is a residual CMD. So what this is basically the observation and the solution, the error. So here we see that in black, there's quite a lot of mismatch. So this is the first result, and then this is after you count for the line of sight depth. And you can see that the error has significantly decreased. So here is my result. So in pink is the SMC star formation history, the line of sight depth added. In blue is a result you've already seen, the LMC's Northern Arm star formation history from Luis Lara 2020. And what you can see is that from 2 gigayears, we have synchronicity between the shell and the LMC's Northern Arm. At 2 gigayears, 1 gigayear, 450 million years, 250 million years. Now that might seem like numbers, but this aligns so well with what we know of the MC's orbital history. So 2 gigayears ago, the MCs had a first close encounter. 1 gigayear, 450 million years ago, they had pericylinder passages, which induced star formation. And 250 million years ago, last pericylinder passage and Magellanic Bridge formation. So now, with all this context, we can say 1, the shell has formed due to LMC's influence. We're quite sure of that. 2, did it form 250 million years ago in a recent star formation burst? Or did it form 1 gigayear ago from enhancements? Now, that's a really good question. I think it's really difficult to assess because you are looking at it, directly. It's really difficult to disentangle which scenario is right. But there's so much to say about it because it could be that, so over the last 500 million years, the SMC and the LMC are going through a denser and denser medium, the Milky Way circumgalactic medium, and that is bound to increase make it more likely for star formation to occur. That could be why, the shell is the way it is. The morphology of the shell is a shell-like structure. It could be that the gas has been shocked from the CGM. There's so much you can say about this. So I'm just going to leave you guys with the conclusions. I think I went a bit faster than I wanted to, but just the key takeaway points. So we can obtain star formation history of a single structure on the SMC from SMASH data. And we're in this amazing time now. And we can provide insight onto the formation history of that structure over the last 4 billion years. For the first time, we have considered the SMC's line of sight depth in its star formation history. While it's something that has been tested for before, it's not been something that's been incorporated in the results. So that's a really cool contribution. And our observation of constraints agrees so well with dynamical models of the recent interaction with MCs. Whether or not the shell formed 250 million years ago as a of a density or of the last 1 gigayear, I think if we had a bit more work needs to be done on the recent oh god, what's the word? the dynamical models, the recent pericentric passage models, and including Milky Way CGM and all that stuff. So yeah, thank you for the opportunities to talk about this.
Thank you. Questions for Joanna? We'll start here. Roger, then we go to Claire.
Thank you. Really nice talk. That was cool. Can you say anything about, so everyone so far has shown synchronized bursts in the SMC. Do you have any sense yet of whether there's anywhere you don't see them?
Right. Any sort of, so spatially or age?
Same thing, kind of. I mean, anywhere spatially in the SMC where you don't see the synchronized bursts.
Right, yeah. There are definitely regions where, well, I guess the way you obtain a global star formation history is by combining spatial star formation histories together. So, for example, the East might have more star formation than the West, and that could look like it's canceling out. So for that, that is, yeah, so I have like a map of the spatial distribution of the mass formation and stuff. So there are definitely regions where you do see that, yes. But I haven't really thought about which ones, and I haven't really sort of discussed that more. But that's a really good point, yeah.
Hi, Joanna. Awesome talk. I really enjoyed it. Can you go back to your preliminary map of the line of sight depths?
Yes.
Yes, this one. And so I'm wondering, what about the different regions of the SMC make the, like, because, you know, in the southwest of the SMC, we know the line of sight depth isn't 0. So is there something that's happening with
I
the
knew
red
I'm going to
clump?
get right. So I'm kind of still thinking about this and I've been thinking about it for months and months on end. Of course, it's not like the line of sight depth there isn't 0. There is line of sight depth, but when we get the star formation history, to compare apples to apples, we take the observed and the model. And when we compare the two, we also simulate crowding. And I think when you simulate crowding, so how crowded the stars appear in the sky, you also simulate a bit of line of sight depth. So in these regions, even though there is a line of sight depth, it could be the crowding's quite, the crowding simulates enough of it, so you don't quite see it as much. But here, a lot of this stuff is because of the tidal disruption of the double red clump. So here, the red clump has got 2 sections. We've talked about it today because of the tidal disruption. So it's way easier to pick up on this. So yeah, so I think that's what's going on there.
Cool.
Okay, I'm going to give Andy and then Christy, and can I get Claire to come and set up?
Thanks, really nice talk. Did you look into whether the Magellanic Stream or the LMC stream could be related to this shell of stars? The reason I ask is it was on that top left northeast corner of the SMC, and that's exactly where the stream comes in. And I just wondered if you looked at that. You talked about the bridge, but could it be related to the stream as well?
That's a really good point. I'm not a stream expert. I haven't really looked at the stream in much detail to make the link, but I'll definitely look into this now. That's a really, really nice point. Thank you.
Yeah, it's the same corner of the galaxy.
Yeah,
that's really all I'm saying.
No, that's great. No, that's a really good suggestion. Thank you.
Nice talk, Joanna. I've got 2 questions. One's kind of a technical one. Do you know, I don't know if you can speak to this, do you know how they modified the code in order to include line of sight distance as part of the fitting process?
Yeah, so all I did was I get the star formation history, so that's separate. And then I wrote a separate set of codes that estimated the line of sight depth from the red clump by isolating the red clump luminosity function and iteratively injecting a line of sight depth in the model CMD. So it gets so it increases, and then I have like 250 iterations on a thing. It's
I see, I got it. Okay, thank you.
And then I redo it again, but then I add that line of sight depth in.
Okay, and the second question is, with the shell structure, I mean, you have in the CMD you showed, you have stars of all ages in there. And so is it the idea that it formed just the last 250 million years or a gig year ago, or that there's stars that have been pulled out from the SMC, and then in addition, there's been a burst that's been triggered by.
Yeah, yeah, that's a very good point. So we discussed all of that in the paper that we submitted, but this is the kind of thing where you can't really say with 100% certainty. You just have to kind of think, oh, there could be a contribution to that. It's a scenario we don't exclude, but we think it's a bit more likely that because of the smaller amount of older populations versus all the young star formation, we think it's just a bit less likely, but there was definitely contribution. So it's definitely a mix of everything. It's just, you know, given what we know about the MC's recent interaction, it's a bit more plausible that it formed in recent times in situ.
So Christy McQuinn, I'm here to talk about the Nancy Grace Roman Space Telescope, which is due to launch in about 2.5 to 3 years, which in terms of sort of mission development life cycle, that's kind of like yesterday, right? So I want to, at least how I feel. I want to give you a little bit of an overview of Roman. Some of you may not be as familiar with its capabilities, with a little focus on what's possible with local group and nearby galaxy science. And so Roman has a mirror that's similar to Hubble's, so in size. So we're going to get the same image quality and sensitivity that we're familiar with Hubble, but the biggest difference is the field of view. So what I'm showing, yeah, there we go. This is the pillars of creation footprint imaged with C3 IR on Hubble. And as we're zooming out, this is the field of view that we will get in a single pointing with Roman, right? So we're going to see the field of view bounded there by white. So it's about 200 times larger in a single pointing than the WIF C3 AR field of view. So even in just one pointing, Roman is the survey telescope. But the telescope was also designed to have a very fast slew and settle time. So it's going to be able to tile parts of the sky 1,000 times faster than Hubble. And so the tagline here for Roman is that we're going to get planets by the thousands, stars by the billions, galaxies by the millions, fundamental physics, and the unexpected. And I did not write that. This sounds great. Okay, so there's a single pointing in Hubble, and you know what? I think often like the high redshift universe, we think about the big surveys, the ultra deep field. You've got to get over cosmic variance and statistics. But in the nearby galaxy world, size of view matters too, right? I mean, things are big on the sky close by, and so this can be really powerful for many of our science. It's just to give you some scale for a local group system. This is Andromeda. Here's a single footprint with Roman. There are 18 individual detectors, which you can see there. Fat covered Andromeda, part of Andromeda with over 800 HST pointings. And, you could do the same scale, or actually the full stellar disk, main stellar disk with, half a dozen to 10 pointings from Roman. The image quality, though, is just as nice. So you can see just a couple cutouts here. You're going to get resolved stars, a little bit of some dust clouds, a young star cluster. So lots of resolved stellar populations. The wavelength coverage is a little bit different than Hubble. So these are just the filters that Roman includes. On the blue side, it kisses up to the optical. So the bluest filter is 0.62 microns. The reddest is at 2.13 microns, right? So you've got a little bit of the optical and a lot of the near infrared. And Roman also has slitless spectroscopy, which is not as much talked about, but you're going to get GRISM and PRISM slitless spectroscopy over the same field of view. So super powerful. Just for fun, we made a gift of the LMC. This is thanks to Claire Squared. I don't even know how to like Claire Murray and Claire Ferretti. They both contributed to making this plot. This is a Pan-STARRS image of the LMC overlaid with 15 Roman footprints sort of marching across the stellar disk, right? And so just gives you a sense of, how much you can do. And the Skilla program, Claire's the PI of this program. We've just heard the results from both Roger and Claire Bruheni on it. All of the Skilla pointings for all of the work we've done fit in like a half or 2/3 of one of those footprints, right? So it's just gives you a sense of scale. It's really just a fun little gift. Okay. I'm also part of the Roman Nearby Galaxies collaboration, which is thinking about what can you do with Roman when it launches. And this is coming out of that collaboration where we've done some simulations on what's possible. The left, we're now getting out of the local group, showing you a fire simulation of a local volume galaxy. And with on the left here, about a half a dozen Roman pointings overlaid. It just sort of gives a sample of what we're going to be able to look at. So in this one image, you've got coverage of the stellar halo, a satellite galaxy, a disrupting satellite, stellar streams, et cetera. And on the right here on this plot, I'm showing kind of a simulation of what the data quality might look like. You've got a beautiful CMD that goes down below the horizontal branch. We've tried to make these simulations realistic. So we've also got a galaxy catalog from candles, those red points, and it just kind of highlights the quality of data that we're expecting from Roman. So this is going to be super fun for CMD fitting, star formation histories, but because the footprint, mass functions of dwarf galaxies, these sorts of things, but it's also going to be really interesting for rare stellar types, right? If you want to study AGB stars, it's really a numbers game. AGB stars are rare. And so you need a lot of footprints in order to be able to build up statistics. So lots of science is going to come out of this. It's by nature a big data telescope, right? It's got a survey. One pointing is already a survey, but we're going to have lots of pointings. And this is just a schematic of, in the top here, in the 30 years of data that Hubble has taken, we've generated 172 terabytes of data. And in the 5-year primary mission for Roman, we're going to have 20,000 terabytes of data. And the telescope has just gone through thermovac testing. And through this process, we've generated more data than all of the Hubble and JWST archives combined, right? And this is just in thermovac testing. So I say this because as the community, we need to be thinking differently about how we interact with this new NASA flagship space telescope, right? It's not going to be business as usual. We can go into mass and put our little things in the shopping cart and download our data, right? You can't do that anymore. You're going to have to interact with the data. You're going to have to come to the data. So the data is going to be hosted on the cloud, and you're going to be able to access it through a science platform and have a lot of the analysis and tools be done in the cloud in a centralized way, because it'll take you weeks to download any of the data. Okay, but Roman is different in other ways, and I want to just spend a couple minutes talking about this. It's a survey space telescope that's community driven. And so what are those those words those are words, but what do they mean? Well, the Roman has a couple specific science requirements from NASA. And the telescope was designed to answer questions on dark energy, the expansion of the universe, like supernova cosmology, and exoplanets, as well as some transformational astrophysics. But the first 3 science requirements here, we need to make sure that the telescope is getting the observations to study these three things. And so 75% of Roman's time in the first 5 years are dedicated to what are being predefined surveys to address these questions, right? But the surveys are being designed by us, right? The community. They're not being designed by NASA. They're being designed by everybody. And so I'm just going to give you a little flavor, a picture of what that might look like. Here's an all-sky map. And so, for example, when you want to study dark energy, you want to look out of the plane, you want a high latitude survey that covers a big area of the sky, shown here in red, in order to measure like BAO or weak lensing signatures. If you want to do, supernova cosmology, you might look at a smaller point of sky, but you want, multi-band time domain observations in order to measure your supernova and your expansion of the universe. And if you wanted to study exoplanets, you might go to the galactic bulge with high time cadence observations in order to get really well sampled light curves for microlensing and exoplanets, right? But so we're defining these 3 surveys to answer these questions, but they're being designed by all of you. So we've got some committees that have been put together. We've had science pitches and white papers in the community on how these things should be designed. Because if you think about it, if they're optimized in a way that everybody is input to, they're not just going to address these science questions. You could also go, say, dwarf galaxy hunting in this big wide area survey as an example. 25% of the rest of the time is going to be open to the community. And one of the things that has been decided is also to do a galactic plane survey of some of that time, about a month. So there's going to be, if you're interested in galactic plane work and resolve stellar populations, that's also on the docket. And the rest of it is going to be open for calls for proposal. And so there are lots of ways to get involved with Roman in this community-driven mission. I'm just going to mention a couple of them, but I'm happy to talk about this with anybody. The core community surveys, we do have committees that are trying to wrangle all the information the community is input, but there's room for more input if you want to join a survey working group. The galactic plane survey as a concept has been accepted, but we're now starting to solicit science input. Where do we point in the galactic plane? What's the cadence of observation? What are the filters? How deep do we go? Do we do the whole thing? These are the kind of questions that you all get to decide upon. And we're also accepting self-nominations for the committee that's going to wrangle all that information together. There's a Roman science interest group that meets once a month that you can keep up to date all things Roman. There's an advisory committee to Space Telescope that we are looking for a couple of new members on this. And there's a conference coming this July at Caltech in the summer that is about Roman with theory meets observation, I think the theme of it is. So there's lots of ways to get involved. This is just a few of them, but I want to make sure that it's on your horizon and on your radar, because in order to make this the most impactful telescope that we can, it really is depending on input from all of you. Thank you.
Oh, thank you, Christy.
I went over.
Oh, not at all. You did not?
Good.
Questions?
Good.
Eugene.
And go light. I've only been in the job in a month, so go light on me.
What about the astrometry of Roman? Would there be single epoch observations only, or there might be surveys which actually have several years of baseline?
Over the lifetime of Roman? So the prime mission is 5 years, which is where we're covering all these core community surveys, but it's likely to last, probably 10 years or more. It's all about combustibles and fuel, but it is actually possible to refuel Roman. And so who knows, it could actually last longer.
And the astrometric accuracy should be good enough to do like proper motions of faint stars in that case?
Yes.
Kat Barger, Texas Christian University. So with this idea that we'll have to do all of a lot of the processing on the cloud, I imagine that there's a lot of thought being put into like the software and the interface and all those things that sound like a nightmare.
Yes. To all of the above. Yeah, I mean, to be honest, to be brutally honest, yes, it is hard and complicated. And one of the challenges with Roman that the community should really be aware of is that it is a cost cap mission, which means that all of those cost overruns from JW and the extended timeline where Congress and the government says, don't do that again. And so Roman is on the hook for delivering everything on time and on budget. And the budget is rather modest compared to what JW got. So the science platform, as we call it, where you're going to be interfacing with the data, has not been scoped in a budgetary way and in really what you would want in order to build out the tools that I think would be necessary for a wide breadth of science. So it's modest. We're looking for ways of finding additional funding to build that out in a more robust way to offer more rich functionality. But I do think we need to manage some expectations that you're going to come to the cloud to use the data. And depending upon the funding climate and how functional our federal government is, we may or may not have as much rich functionality that we would like to offer the community. And that's really what it is, right? It's, as we all have gotten those of us have gotten Hubble budgets this past week, recognize that there is a very tough funding climate right now for NASA. So we're going to deliver the best we possibly can. And I don't think it's going to be enough because we're constrained, to be perfectly frank.
A question over here.
How good is the astrometry compared to Gaia?
Okay, so I'm going to need some help from my proper motion friends in the room. There you go. That's the right man to ask right there. Here you go, Roland. who was the previous mission head of Roman and a proper motion expert. So you're really getting the person who knows the answer to that.
Thank you. Roland van der Marel, Space Telescope Science Institute. So first of all, let me point out that there is a white paper about astrometry with Roman on the web by Robin Sanderson and Andrea Bellini that's been there for a few years that lays out all sorts of things that you can do with accuracies, whatever. So go there if you want any details. In generally, proper motions from space are fantastic. I'll talk tomorrow about JWST and Hubble, but we can do as well as Gaia, 10 magnitudes fainter, if not more. But it's over very small fields. Now, for Roman, you get huge fields, but you have no time baseline. So to do as well as I just said, you need 10, 15-year time baselines. So in the beginning, you're not going to get much. To answer Eugene's earlier question, for example, the high latitude survey, for the GRISM observations, you do actually need to observe at different roll angles, which means that you need to do it at different times. So there will actually be a time baseline built into some of the surveys automatically. But to do really good proper motions, you would have to come back after 5 or 10 years and re-observe fields. In the beginning, what you can do is you can have fields in compared to Hubble archive, but then you're dominated by the fact that the Hubble fields are really small. So the potential is great, but the time baseline will just have to build up.
So we're kind of cutting into our next session, but I'm sensing a lot of interest, so I'm going to give one more. Okay, Mariaros, all you.
It's a bit of a provocative question here. So assuming we are not ready to interface with this great platform, are we going to be ready to preserve the data, that amount of data properly for?
Like preserve, you mean store?
Well, yeah, so they don't change, they don't alter, because we will have to develop new techniques to interface with the data, right? But we want to make sure nothing happens to the data, that they are acquired properly, and yeah.
Right. So
that's in the budget.
Yeah, Rachel, if you're itching to answer this, but I would go. My first stab at it, and then Rachel, can you get some of the technical details? Is that yes? So the idea here is that we're taking the data, we're going to download the data, and we're going to process it through calibration and eventually mosaics and catalogs as well. That will be done at the Space Telescope Science Institute, and that will be redone with a certain cadence. So like right now, HST, you can, you download the data and it's reprocessed with the latest calibrations sort of on the fly. And Roman data is going to be too big to do that. And so, you're going to build up calibrations and you're going to do more of a data release where you're reprocessing everything that's been taken and releasing it to the community, unlike the new, the new whatever calibration fields and files we have. So it will not be a rolling data release like we're used to with Space Telescope, with JWST and HST. It'll be more of a points in time of like, okay, we'll trigger it through something in the survey has been completed, and now it's time to reprocess that part of the survey and release it again to the community in a data release. But we will be storing all of that. Yes, we will be keeping all of that information and the data. But Rachel, do you want to add anything to that? Rachel is a key member of the Roman Telescope branch at Space Telescope. So
yeah, so Rachel Beaton, Space Telescope Science Institute, everything that's in the cloud will also be on-prem, on permanent on-site storage. And actually, once the data is in the cloud to cloud transfers. So maybe you can't use that platform, but if your institute has a cloud platform or you have AWS Magic Buckets, that is feasible. So all of that will be happen.
We're still working on that.
Yeah. Oh, okay. So we have a requirement to turn over data on a set cadence. So like images become available, then stacks, and then catalogs. But right, like Christy was saying, there will be some timed reprocessing, because that's what weak lensing probably wants. But all of those pipelines, we're getting ready to go so that that torrent of data is coming through and science is maximized. So that's like what I do with half my time or more.
Yeah, and so just curious, I mean, what we're currently, this is still all in development, but we're currently thinking about once we get new calibrations, not necessarily to hold on to the stuff that's been previously calibrated, but only keep the newly calibrated stuff, but it'll be coming out in data releases. And so like now you're turning it over and we've got a new set of data.